In this video, we're going to talk about parameterized surfaces, but to begin, we want to remember how to parameterize. Not that we don't do it on every single instance possible, but we're going to parameterize this counterclockwise spiral. Okay, so I have a little drawing of this, and again, know that parameterizations are not unique, but I want you to develop a parameterization. So pause the video, try it out. Okay, well, hopefully you pause the video. And my parameterization, not to say that yours is incorrect, but the one that I have is, well, and we're in R2, so we need two dimensions, right? So I did t cosine of t and then t sine t. And then we have to specify that t here is within 0 and infinity. Okay, or it's from 0 to infinity. Okay, so again, your parameterization could certainly work, but you probably need some form of cosine and sine in there to get that spiral effect, and then some multiplier of t to make sure that it expands as you go out. Okay, so parameterizations, and like I said, we're going to talk about parameterized surfaces. So we've talked about parameterization. Now we need to look at surfaces. So we've seen these represented kind of in two ways. One of which is just looking at, say, the graph of z is equal to, and then writing z as a function of x and y. The second one was to maybe look at a level set where it's as a function of three variables. So in the case of the first kind, where we said z is equal to a function of xy, we maybe looked at a paraboloid, for instance, just said z is equal to x squared plus y squared. Okay, versus the level set approach, okay, we do have something that involves x, y, and z, so it's actually a function in 4 dimensions, right? And we set h equal to 1, so we get rid of that 4th dimension, and then we just look at 3 dimensions, so we get something like a sphere. Okay, and so now we want to look at parameterizing these surfaces, because we can certainly parameterize in R2 to our heart's content, but we need to be able to look at higher dimensions as well. Okay, so some definitions. Okay, we're going to say let D be an open and connected set, so make sure we get those assumptions in there. Okay, so we have to have open and connected, and we don't really care too much about the boundary, but it could include the boundary. It might just include some points. Okay, and we're going to talk about a parameterized surface as being a continuous function. Okay, great, and we're going to use vector x to denote that parameterization, or that continuous function. Okay, and we need to be one-to-one. Okay, most of these are, and you don't have to do too much thinking, but just be mindful of that. And then in that case, that continuous function that we develop is our parameterized surface. Okay, and when we look at that connected set, that open and connected set D, and we run that through the parameterized surface function, that's called our image, or the parameterized surface by x. Okay, so now I have an example here. Okay, it's a function of theta and phi. Okay, and it's saying that theta goes from 0 to 2 pi, phi goes from 0 to pi, and then we have a lovely combinations of sine and cosines. And I'm going to say that you might recognize this from back in the day when we were talking about spherical coordinates, but this is just a sphere. Okay, and more specifically, it's a sphere of radius 1, centered at margin. Okay, this example is going to come back over and over and over, so I would suggest that you get familiar with it. Okay? Okay, well, let's keep doing some examples. Okay, I want to find a parameterization for a disk of radius 2 that where the disk is in the xy plane, but knowing that we're in 3 dimensions. Okay, so let's see. As I think about it, disk of radius 2, we know that that can be 2 cosine of t and 2 sine of t, but that actually just describes the boundary, right? So we have this parameter t, and so we don't really want just 2. We want to be able to use any value, so I'm going to insert another value s here, and then the third component is going to be 0 if it's in just the xy plane. So I'm going to say s of s and t. Let me make that into a better x. And we're going to say that, that s is in the domain 0 to 2, and t is in the domain 0 to 2 pi. Okay. Alright, next example, parameterization for the plane spanned by vectors u and v, which goes through A. Alright, well, this one you might remember from way back when we were discussing this in Calc 2, but we can actually write a plane, the formulas of plane in parametric form as, well, we have to have a point on the plane, and then we just add a multiple of the 2 spanning vectors. T, v. Okay? And then we just say that the parameters s and t are real numbers. Okay? Next example, we want to find a parameterization for a cylinder of radius 2 centered on the z-axis with z being 0 to 3. Okay? So this, to me, when I see this, that automatically means that one of my parameters is going to be s, and we're saying that s is within 0 to 3. Okay, now I got to think about this. Okay, well, I know if I want to use 2 parameters, and this also, so I haven't been checking for open connected sets and all that stuff, so we'll do that here in a moment. Okay, so if the cylinder, we're assuming that it's not a solid cylinder, so we can just say that this is going to be, if we look in the xy plane, it should just be a circle, so that's 2 cosine t and 2 sine t. If it was a solid cylinder, we would probably need a third parameter here, just so that we know we have something to go not just along the boundary. Okay, and then let's see, so that gives us the xy, and then I need another parameter in the z direction to account for that 0 to 3. Okay, and then we need t to be within 0 to 2 pi. Okay, so I haven't been checking open connected set. Generally, we don't need to, but we're checking that again, that domain D is an open connected set, and so really that's just checking, okay, well, is our S and T on an open connected set? And if you look at this, that creates a rectangle, so it is open and connected. Okay. Alright, and then now, before moving on, I want us to do some thinking. So if I have G as this function on domain D, that's a continuous scalar valued function, how can we parameterize the graph of G? And I want you to pause the video and just think to yourself for a moment about this. Okay, for time purposes, I'm just going to press on, and really all we need to do is say that, okay, well, we're still going to need a parameterization of S and T, and say that, well, maybe the first component we can write in S, second component we can write in T, but then I'm out of parameters, so I need to say that the third component is going to be a function of S and T that we send through G. Okay, so in the next example here, okay, we want to parameterize the paraboloid for z within 0 to 1. And so one parameterization that exists using our above idea, okay, s and t is equal to, okay, well, if I do s in the first component, t in the second component, well, then the last component is going to be s squared plus t squared. Okay, and I need to allow s. So now I need to make sure to define my parameter, or restrict my parameters rather. So s can be within -1 to 1. Okay, because we want z to be between 0 and 1. Okay, but then for t is actually going to be dependent on s, and specifically, if we know that s squared plus t squared has to equal 1 at most, then we actually get 1 negative square root of 1 minus s squared is the lower boundary, and the upper boundary is just going to be the positive version of that. Okay, so this is one way to parameterize it. You could also maybe use, say, a familiar r and t, and say that this is r cosine t, and use kind of polar, or use polar to parameterize this, r sine t. And then for the third component, it'd just be r squared. And then you can say this actually ends up working out a little bit nicer. R is within 0 to 1, and then t is within 0 to 2 pi. Okay, so with all these, there isn't necessarily a unique parameterization. You could parameterize any of the examples that we did in different ways and still get the same surface. Just make sure that, well, I guess, A, check your answer, but B, know that your answer might not be necessarily the same as what others get.